I mentioned before that current can't be used up in an electric circuit, and I'd like to go into that in a little more detail. So, current is never used up in a circuit. Okay, so just to remind you, I can draw a simple electrical circuit like this where we have one bulb and the bulb will light up. Okay. Well, I could create another circuit where I have two bulbs in series. So what that will look like is 1, 2, like this. And each of the bulbs will light up, but not quite as brightly as the one in the one bulb circuit. Okay, so this is bright in the first case and dimmer in the second case. All right, and you can measure the current at different places here. So you could have current here and current here, and you find that the current is constant throughout. Okay, so measuring before or after the bulb doesn't matter, you get the exact same amount of current. All right, well, if you do the same thing and you measure the current at different places in this circuit, what you'll find is that there's some current here, and some current here, and some current here. And again, the current is the same throughout. Or let me say the current is constant throughout. But smaller than the one bulb circuit. Okay, so the currents that I've drawn in purple are all equal to each other, but they are a smaller amount than the ones that I drew in blue. So when you change the circuit, you can change the amount of current that there is. But within each circuit, there's going to be the same amount everywhere. Okay, similarly, if I draw another circuit with 3 bulbs, the pattern continues. So I can have 1, 2, 3. And if I do that, then what I find is that each one is dimmer than in the 2 bulb case, but still lights up, and they're all equally bright to each other. So this is dimmest. And again, the current is the same throughout the circuit, but it is going to be smallest yet. So if I draw currents at all these locations, then there's no change from one spot to another. So again, the current is constant throughout. But smaller yet. Okay, so there's 2 rules here which only sound confusing because we use similar words, but the actual rules are not confusing. In each circuit, the current cannot be used up. So any current that's before a bulb is the same after, and if there's only one path, all the current has to go through each item in turn. But depending on what you put in a circuit, you could have more or less current throughout the circuit. So sometimes there will be a lot throughout the circuit, sometimes there will only be a little throughout the circuit, but it's the same amount no matter where you measure it. Okay, so how can we think about what's going on here? Well, one model that you might come up with is that each of the light bulbs is essentially an obstacle to the flow of current. Okay, so current is trying to flow in each case, but it is harder in cases where there's more bulbs. Okay, so the idea that we're talking about is resistance. Okay, so we have some resistance when there's one bulb. We have more resistance if there's 2 bulbs. And we have the most resistance if there are 3. Okay, so quite literally, the bulbs are resisting the flow of current. They're making it harder for current to flow, which means less current flows. Okay, another thing to notice is that it seems, based on these three cases, that the brightness of the bulbs corresponds to the current. So if there's more current, then they're brighter. If there's less current, then they are dimmer. Okay, and that's something that we will use in more cases. Now, notice that the battery is the same in each of these three circuits, but the amount of current is different. So don't be confused. Batteries do not provide a constant current. If you have a battery that's not part of a circuit, it doesn't provide any current at all. What a battery does, as we learned earlier, is provide a potential difference. And so the potential difference across the battery will be the same in each of these three cases. But the amount of current that results is going to be different because according to Ohm's law, as we add more resistance, we get less current in each case. Okay, so the name of this video is Kirchhoff's Junction rule. Kirchhoff was a German physicist who came up with some rules for studying electric circuits. And what the junction rule says is basically the same thing as current is never used up in a circuit. So the junction rule says, like I said, that the current doesn't get used up, but it says it in a slightly different way. So let's say we have a place where multiple electrical branches are present. So we could have some amount of current that flows in and some amount flows out and some amount flows out. Okay, so if we have I1, I2, and I3, just naming those three, then what the junction rule says is that because current can't be used up, any current that goes into the junction, so I'm adding up all the currents in, will equal all of the currents going out. Okay, so any current that goes in has to go somewhere. So in this case, as I've drawn it, I1 is the only one in, and that's got to be equal to I2 plus I3. So essentially, the current splits. So some of it goes down I2, some goes down I3. It almost certainly does not split 50-50. So you cannot assume that it is going to split in half. But what you can assume is that I2 plus I3 will add up to be I1. How it splits depends on literally everything else in the whole circuit. So you can't tell until you actually do some calculations. But you do know that this relationship will be true. Okay. In other parts of the circuit, very likely, the current will come back together and that rejoined current will be larger. But what never happens is current getting used up or appearing when there is a component. So no matter what the component is, even if it's a battery or something like that, if there is current coming out of the battery, there has to be an equal amount of current going in. Nothing just generates current out of nowhere.